Hello students, welcome to Inside Physics. I am Srinivas. Today we are going to discuss about interference in wave optics. Wave optics is the study of light which we will study the wave properties because light is a form of electromagnetic radiation and it propagates in the form of waves. Sometimes it behaves like a particle and sometimes it behaves like a wave. So we will see some brief introduction towards the interference. So in 1678, Huygens scientist propounded the theory of wave theory of light. So he said that light will be propagating in, in the form of waves. But he could not tell anything about the wave nature or velocity of light or the details he could not tell. That the details means whether the wave is a progressive wave or longitudinal wave or a transverse wave. The details about the wave theory he could not tell, and doesn't tell anything about the speed of the light or wavelength of the light light waves. So in this way he just proposed a theory that on the basis of his observations that light travels in the form of a wave. But later in 1801, okay, so later in Thomson, he done the experiment of double slit interference experiment. Okay, so he did the experiment to find the wavelength of light. So, okay, so double slit experiment. On the basis of that experiment, he could produce the interference of light and he could be able to calculate the wavelength of light. So after that experiment, actually, the wavelength of light was found because of the experiment done on the interference of light. The experiment was Thomson's double slit experiment. Okay. So actually, the interference to get the interference of light is very difficult. With ordinary lights putting together two ordinary lights and they cannot produce any interference. To produce interference, there should be two sources of light and they are coherent sources. They should be coherent sources of light. Coherent means they should be same in frequency. The frequency of waves should be same and the phase difference of that light waves should be also constant. The phase difference should be constant. Then they are called the coherent sources of light. So the coherent sources of light can produce the interference pattern. Generally we observe the in the vivid colors, the different colors of a thin film. That means a soap bubble or an oil sprinkled on a water puddle. We observe generally in our daily life. They will they will show different incandescent colors. That is because of the interference pattern. So that is the interference of in thin films. Okay, the study of interference in thin films has actually a lot of applications. Okay, in like interference filters, interference mirrors. So these pattern of interference in thin films is also explained by Thomson with his experiments. Okay, so this is the brief introduction of interference. Now we will see what is the process actually. What is the process of interference? See, when two waves, light waves, are starting from two different points and they are meeting at a point P. This is S1 and S2. So to form an interference pattern, actually these two waves should be having same frequency and the phase difference of these two waves should be constant. Then these two sources of light are called coherent sources. Okay, these two coherent sources are formed with single source. Okay, so then the coherent sources will produce two light waves, two or more light waves. They will be forming and interfering. They are touching a point here at P by forming the interference pattern. Okay, next, if incoherent sources cannot produce interference pattern. So incoherent means they are actually opposite in phase. The light waves are opposite in phase and they are said to be out of phase. Okay. So here the interference pattern is formed due to the coherent sources of light. Generally we observe here, we take two cases in interference. They are, first one, the constructive interference. Constructive interference. So in constructive interference, actually two waves, if two waves are crossing each other, so the when they arrive at a point, suppose two waves are crossing each other, and when they arrive at a point, okay, so here when the constructive interference should be taking place, so when we consider a point here on this, because of the laws of superposition, we can say that the disturbance at this point, disturbance at that point is the sum of the individual disturbances of this point, of these two waves. Okay, we can say that the disturbance at this point can is equal to the sum of the disturbances, individual disturbances of two waves. Okay, then if they are adding up the disturbances and they are having an amplitude a, so in that case the the resultant wave will be having the amplitude of both the waves. If it is having an amplitude a, if it is an amplitude a, and this wave will be having an amplitude of a plus a, that is equal to 2a. So if they are two waves are moving and they are overlapping while crossing each other, they will superimpose on each other. So with the principles of superimposition, we can say that these disturbance created by these two waves will be summed up. So if a wave has to be, two waves has to be formed a constructive interference, so that means they should have the crust to crust correspondence and trough to trough correspondence. That means crust to crust, trough to trough. Okay. So in this way, the constructive interference will happen. So when a constructive interference is happening, we know that intensity of the interference pattern, the fringes formed, is directly proportional to amplitude square. Okay. So here, if the amplitude is A, and we know in constructive interference, the amplitude will become A plus A. That means the intensity of the bright fringe here, because of the constructive interference, bright fringes are formed. So here it will become 2a whole square, that is equal to 4a square. 4a square. So 4a square, that means the intensity has become, you can say 4i, that means I proportional to a square. But if you add these intensities individually, I plus I, suppose it is 2i only. So the resultant intensity is more than the individual intensities when the constructive interference is happening. Okay, so this is when the constructive interference is happened, the bright fringe will form. Okay, so if the constructive interference, the bright fringe should be formed. See, the phase difference of the two waves must be 0, 0, or the integral multiples of 2 pi. Okay, integral multiples of 2 pi. That means, see, when a bright fringe is formed at the center and another bright fringe and the next bright fringe, in this way the bright and in between the dark fringes are formed. The center point is called the axial point, a bright spot here. So when the two waves are arriving with zero phase difference, the bright center spot fringe will be formed. And when they are having a 2 pi radians of phase difference, that means the second wave will be crossing the first wave with a difference of the difference of wavelength, one wavelength difference. Okay, so if the path difference is one wavelength, then we can say it is they are both having a phase difference of 2 pi. So we will see the terms, what is phase difference and path difference. So first of all, this is the constructive interference. Next, we will move to destructive interference. What is a destructive interference? So here, if the waves are crossing each other, if the waves are moving, okay, and if they are arriving at a point, if they are arriving at a point with the crust on other side and a trough on the opposite side, so they will be having a trough, crust to trough correspondence. Suppose we need to draw a little bit differently here. So they will be having, suppose these two waves are arriving at a point, that means P. So they will be having a correspondence between them. What correspondence? See, they will be, this is a trough and this is a crust, this is a trough. See, what is crust, what is trough means? In a wave, the upper part which is showing like this is called a crust. The lower part, it is moving in the down level, is called a trough. So the trough to crust, trough to crust, crust, trough to crust, crust to trough, trough to crust, crust to trough. The correspondence, the matching of the waves will be like this. In this way, they will be are having an phase difference of 180 radians. Okay, that means pi radians. That means they are out of phase, they will be said out of phase. by pi radians. So in this way the destructive interference will be formed. The destructive means there will be not be any bright light, there will be a dark fringe. Fringe means the circular form of a distribution of light. So the fringe, the bright fringe means it is the light is having a circular bright path. So the dark fringe means in between the bright fringes there will be a dark space. That means there is no light intensity there. The dark fringe means the light intensity is zero. Bright fringe means there will be a light intensity. Here the amplitude, if the both waves are moving and crossing each other and they are getting superimposed, the amplitude means with the help of law of superimposition we can say the resultant amplitude is a plus a, right? The resultant disturbance is the sum of individual disturbances. So here the amplitude is this is a, this is minus a. That means the sum is a minus a is equal to 0. The resultant amplitude is 0. If a is 0, with this equation I proportional to a square, we can write the resultant intensity is 0, right? So if the resultant intensity is 0, the light intensity is 0, that means there is no light. The fringe is dark, that is called dark fringe. With the help of this destructive interference, so a dark fringe is formed. So here when the waves are moving and they are having a phase difference of 0, pi, 2 pi and integral multiples of pi and 2 pi, they are forming the constructive and destructive interference in a sequential order. That means a bright spot, a dark fringe, a bright fringe, a dark fringe, a bright fringe, in this way. This is the interference pattern that will be formed by the superimposition of light waves coming from a two coherent sources. This is very important. The incoherent sources cannot produce interference. Suppose in a generally we observe in our houses also, there will be, if you say there are two light sources, there are two LED bulbs in a room. So they are also sources of lights, two sources of light, but they cannot form interference pattern because their intensity of light, if you switch on both the LEDs in a room, they will be having I plus I, that is 2I intensity of light, but they cannot form interference because there will be a fluctuating phase difference is there between the light sources, the light waves emanating from the two light sources. Okay, to see what we have to do to get the interference means to get a two coherent sources. How to get the two coherent sources of light? There are instruments like Lloyd's mirror, okay, and Lloyd's mirror is one thing which will be useful for to get the coherent sources of light. Coherent source, okay. And in double slit interferometer experiment also we are getting two coherent sources of light, okay. So this destructive interference and constructive interference are the general phenomena of interference where we can get the bright fringe and dark fringes consecutively, okay. Actually what is interference means the redistribution of light energy, redistribution. That means when the light waves are getting superimposed, the light waves are redistributing their energy in the form of dark fringe and bright fringe. So okay, so next one, here there are some conditions to obtain a sustained interference. Sustained interference means the interference pattern should be very sustained, long sustained for long time. Okay. Conditions for sustained interference. See, first one, the two light waves should have same frequency. They should be having same frequency. Okay. And the second one, they should be having same phase difference, or phase difference is constant. Phase difference is constant. Okay. Third one, as the light is an electromagnetic wave, so there will be some electric field which is getting overlapped in the process of interference. So in the dark region, the vector sum of electric field overlapping, the algebraic vector sum should be 0. That means the two electric fields are either out of phase or they are in a perpendicular planes. Then only then the dark fringes are formed. Otherwise, if the electric fields are not out of phase, they are in phase or they are in same plane, the dark fringe is not formed. This is the third condition. Sum of electric field vectors is 0. Fourth one, the plane of polarization of two interfering waves should be same. If they are polarized waves and if they are not in the same plane, suppose they are polarized, the plane of polarization is perpendicular to each other, then the interference pattern cannot be formed. That means the plane of polarization of both the waves is same. Fourth one, fifth one, sorry. So the path difference of two waves should be less than the coherence length. The path difference, see, the path difference, we will see what is path difference in the next topic. See, the path difference of two waves should be if two waves are propagating in this way, in this direction, and they are meeting at a point. So when we say path difference, the actual difference of traveling, the length they have traversed, the difference of length they have traveled is called the path difference. The path difference should be less than the coherence length. Coherence length means the distance between the two slits or two coherent sources. Suppose this is D. The coherence length. See, the path difference should be less than the coherence. Then only the interference pattern is formed. So what happens if the path difference is too large? The path difference is too large, the interference pattern is not formed. That means the wave, if the wave is moving in one direction and the second wave will be arriving at the first wave before it is crossing the first wave, that means the interference pattern, there is no way that interference pattern can be formed. And if the path difference is equal to the coherence length of between the two slits, that means the total interference pattern will be vanished. The total interference pattern will be vanished. That means, to if we take some precautions for the experiment we are doing, we actually we should take a necessity step that this length is very small. The difference, the coherence length should be very small, so to form a distinct interference pattern. Okay, so as the two sources are coherent, the the bonds, the bands, fringes formed, the dark fringe or the bright fringe formed will be stationary. Okay, because these two are two coherent sources of light. So the fifth one is the path difference. The path difference should be less than coherence length. That means we can write delta less than L coherence. So these are the 5 conditions to obtain a sustained interference pattern. Okay, so here if you observe, we can see what actually happens when an interference pattern is formed. We can see with two waves. I will explain you with two waves how they are actually crossing each other. Okay, so if it is P Q R and one next one. Okay, it is S, suppose S T U. Okay, so stop up to here only. So see, in this kind of overlapping of waves, the interference pattern is limited to this part only, QR, and if you put T here, this is ST. Okay, so these remaining part PQ and TU of the waves will not be participating in the interference. So QR and ST of the this part of the two waves are only participating in the interference pattern. So here the interference is will not be distinct. If the total wave, that means if they are crossing each other and the total wave from P to R, S to U is participating in the interference pattern only, then a distinct interference pattern will be formed. So if the path difference is too large between them, then there will not be any interference pattern. So that is the meaning of this path difference should be less than the coherence length. So here what we observe is only some part of the waves are getting superimposed. This is the details of conditions what we require to get the interference pattern. Okay, so there are some terms which we have to observe carefully, frequently used in the wave optics or in the interference pattern also. We will see some terms and their meanings. Okay, First one, geometrical path length. Geometrical path length. See, if the two waves are, if a wave is moving from A to B, A to B, and see the wave starting from A and moving to B, okay, the the shortest distance between A to B, actually the light will be traveling in a straight line, okay, in either in a medium or in vacuum, or in medium, a medium to vacuum, or a vacuum to medium, whatever may be the medium, the light wave will be traveling in a straight line, okay. In this case, the shortest distance between A and B is called the geometrical path length, the GPL, okay. Then next, optical path length. Optical path length. So what is optical path length? Generally, when a light is moving from vacuum to a medium of refractive index mu, so the light will be slowed down, the velocity of light will be changing in moving from one medium to another medium. When the light wave is slowed down and the velocity is slightly decreased, the distance covered in that medium, the entering medium, suppose light is entering from medium 1 to medium 2, so here it is vacuum, from vacuum to medium 2, where having a refractive index mu, so the velocity of light will be changing. So in that way, the optical path length, so the difference, if the if it is slowed down, the speed is decreased in a medium, then the distance covered will also decrease. That means the optical path length is denoted by delta is, we can write mu L, okay, or that means L is geometrical path length, that means OPL, optical path length, is mu into GPL, geometrical path length. So here the optical path length will be less than geometrical path length depending on the mu value. So next one, these are the lengths we should be considering while we are considering the wave motion of light waves. So optical path length has very significance in further study in the wave motion of light waves, okay. Next one is path difference. Next one is path difference. What is path difference? See, we have seen optical length, okay. The difference in optical length means the distance traversed by a light wave, the distance traversed or traveled by a light wave. See, the optical length, difference of optical length when the two light waves are traveling in different directions, okay, when the two light waves are traveling in different directions in any medium, okay. So that means path difference is the actual difference between two waves, the optical length difference. Optical path length difference is called path difference. Next one, optic path difference. Next is phase difference. Phase difference, delta. So if two waves are crossing each other, okay, and they have a optical path difference of, suppose, a lambda wavelength, a optical path difference of one wavelength, okay, so then they are said to be having a phase difference of 2 pi. When two waves are crossing each other, okay, and they are having a optical path difference of, suppose, one wavelength of light lambda, then they are said to be with a phase difference of 2 pi radians. That means when a wave is traveling a distance of lambda, one wavelength, so the phase of that wave will change by 2 pi radians. That is the difference. So in this way, the phase difference can be written as 2 pi L by lambda. This L is the length traversed by the wave, the distance traveled by the wave, into 2 pi by lambda. That means in this length, suppose the total distance traveled is L. L by lambda means we are making this length fitted with this wavelength. How many wavelengths, how many number of wavelengths are fitted into this length, into 2 pi radian. Actually this has a meaningful formula. When we, if you understand what is phase difference, that means this L by lambda has a significance, and the number of wavelengths fitted into the this length traversed by the light wave, this is phase difference. So these terms are very useful and we will use in further wave optics study. These are all the terms should be remembered. And the next one is techniques of obtaining interference. So how to obtain interference? There should be some technique, right? So techniques of interference. Techniques to obtain interference pattern. First one is division of wave fronts. Division of wave fronts. So division of wave fronts is a process when we consider a single source of light and it is divided into two coherent sources of light, okay, S1 and S2. It is done in a Thomson's double slit interference experiment. So what he has done is a single source of light emits wave fronts. See, the wave will be traveling in the form of wave fronts like this. When these wave fronts will touch these, entering through these two slits. So here when a wave front touching here, see, touches here, and wave the light wave will be coming from this slit and the slit 2 also, S2. So from these two slits the light wave will be forming like a two sources of light, and the wave front is again divided into two. Here the individual light sources will be emanating wave fronts, like this is just like it is another source of light. So this wave front is divided into two wave fronts, that is division of wave fronts. In this way we can get the interference pattern, okay. So this is done by the Lloyd's mirror, and other interference equipments. Okay, next one, second one, division of amplitude, division of amplitudes. So division of amplitudes, okay, division of amplitudes is a process of, see, when a light wave is reflected, partially reflected, so the amplitude will be divided. Partially reflection, the partial reflections of the light beam into two or three beams. Because of partial reflection, it will be divided into two or three beams. In this process, in the process of partial reflection process, the amplitude of the light wave will be divided into two or three parts. Okay, this is done by thin film interference, that means wedges and Newton's rings, and interferometers like Michelson interferometers. These equipments will be following the process of division of amplitudes to get the interference pattern. In thin film also, what is a thin film? A very small length of a medium, that means thickness, length means thickness, a very small thickness of a medium. If a medium has having a very small thickness, then it is called a thin film. Either it will be a glass or air. If it is having very small thickness, it is called a thin film. So thin film, in a thin film, the interference pattern is actually using the division of amplitude. These are the two techniques used to get the interference pattern. Okay, next we will calculate, we will see some formulas for the interference pattern. Here, see, if two waves, suppose this is slit 1, this is slit 2. Two waves are emanating from two slits, two coherent sources, and they are forming an interference pattern and then meeting at a point P. Okay, they are meeting at a point P. Okay, this distance is D. Okay, so here it is the center of the coherence length between the two slits M, and there will be here, it is O axial point where a bright spot, bright fringe is formed. Okay, these are the lengths. This is D by 2, this is D by 2. Okay, if this distance is considered as x, this distance is considered as x. Okay, this is D by 2, this is D by 2. The interference pattern is formed on this screen. Okay, this is the distance between the interference pattern and the slits. D is the distance. So the point P here, if this is E, this is F, suppose. Okay, So if you observe this diagram, what I have drawn is, from a single source we have taken two slits arrangements S1 and S2. From these two slits there will be two light waves emanating from these two sources of light, considered as coherent sources. Okay, so these two sources are, while crossing each other, they will overlap and they will be forming an interference pattern. Okay, so this is just an example. These are only two waves. There will be lot of other waves also which are overlapping and crossing each other, and they are making an interference pattern on the screen. So this interference pattern can be observed within eyepiece. So okay, so here, first, what is the path difference? What is the path difference? See, S2P and S1P. If you want to calculate the path difference here, we have already discussed the difference of path traversed. The optical path difference of optical path length is called path difference. So how to get that one? Here the path difference is S2P minus S1P. S2P minus S1P is the path difference here. So how to get the path difference? From this, if you observe from this diagram, we can write S2P minus S1P whole square, sorry, S2P square minus S1P square. Okay, is equal to, we can write, see, S2P square, S2P, this distance, S2P. If you observe this triangle PS2F, PS2F, okay. So what you can observe here is S2P, this one, is equal to d square plus x plus d by 2. See, PF, we can write PF is equal to x plus d by 2, right? PF is equal to x plus d by 2. This length is d by 2. In the same way, PE, PE, this is E, is equal to x minus d by 2. So here if you observe, S2P minus S1P whole square is equal to d plus x plus d by 2. Okay, x plus d by 2, that means this one whole square. You understood? D square plus x plus d by 2 whole square is equal to S2P whole square minus, we can write S1P. S1P means, see, d square, S1P, this distance is also d. D square plus this distance, x minus d by 2. D square plus x minus d by 2 whole square. Okay. If you solve this equation, if you can solve this equation, if you observe the terms, what you can understand, d square, this d square plus x square plus d square by 2, okay, and here in this equation plus 2xd by 2x into minus d square plus x square plus d square by, this is actually 4, d square by 4, d square by 4, that means a square a plus b whole square formula, minus 2x d by 2, okay. So here if you solve the equation, we will get here S2p minus S1p is equal to, okay, 2xd by S2p plus S1p. If we solve this equation, we can get 2xd by S2p plus S1p. Okay, d square gets cancelled because this is minus x square gets cancelled. So d square by 4. These two terms xd plus xd will be added up and it will become 2xd. So here I have written this one, how I got means a square minus b square in the form, this is in the form of a square minus b square. I have written this one, see, a square minus b square in the form of a minus b into a plus b. A square minus b square I have written in this form, that means a minus b into a plus b, that a plus b term is coming as a denominator here. I have made a direct step. So if you observe S2p plus S1p, see, with the approximation of S2p, see, when a wave is looking like this to travel, but actually when you compare this path difference, and this is almost equal to d, S2p or S1p, with the consideration of approximation, we can write S2p nearly equal to S1p nearly equal to d. This is almost nearly equal, we can write, because the light will be bending a very small angle, okay. If we write a perpendicular to this one, okay, the theta, the difference, the light wave is making an angle with this length theta, okay. Here S2p nearly equal to S1p is equal to d. In this way we can write 2xd by d plus d, right? That means 2xd by 2d. So that means here see, S2p minus S1p, S2p minus S, the path difference, it can be written as xd by d, xd by d. So the path difference can be written as lambda is xd by d. So this is how we can calculate the path difference when we are considering taking two coherent sources to make an interference pattern, okay. So here next, how to get a bright fringe condition. Bright fringe condition. See, when this path difference, I said, is equal to the integral multiples of wavelength, full wavelength, then a bright fringe is formed. That means xd by d is equal to integral multiple of wavelength. That means we can write m lambda. M here, m is the order of the fringe. That means if here for the center bright spot axial point, m is equal to 0, because here the two waves are traveling with zero phase difference between them. They will be arriving at this point with zero phase difference. That means here the path difference of the two waves with forming an interference pattern at point 0 is 0. Path difference is 0. See, next a bright fringe. See, next bright fringe. Here the axial point center bright fringe, then a dark fringe. The next bright fringe. Suppose the next bright fringe is P. Then the path difference between S1 and S2 will be one full wavelength, one lambda. So in this way we can consider this as a bright fringe condition. Okay, if the next bright fringe, this is order of fringe, m is order of fringe. For the next bright fringe, we can write this as m plus 1 into lambda. Okay, for the next bright fringe, this is the order of the fringe. So in this way, the condition for the bright fringe we have taken. Next, the condition for the dark fringe. Condition for the dark fringe. Okay. See, when the phase difference, the path difference of two overlapping waves which are traversing is an odd integral multiple of lambda by 2. Okay, that means they are out of phase by 180-degree radians. So here the path difference will be an odd integral multiple of half wavelength lambda by 2. This is the condition for dark fringe. Okay, so here if the order of the fringe is m, then we can say if the first dark fringe m is equal to 0, it will be lambda by 2. The path difference will be lambda. For first dark fringe, the path difference between the two waves will be lambda by 2. Okay, and the next dark fringe will be here, if m is equal to 1, this is 3 lambda by 2, the path difference for the next dark fringe. In this way, this condition is useful to get the path difference and the phase difference of the two waves. So for each bright fringe and for each dark fringe, you can get the conditions like this. Okay, next, the fringe width condition for fringe width. That means if the fringe width means the consecutive bright fringes or the consecutive dark fringes. Suppose this is the center bright spot, this is the first bright fringe, second bright fringe, and third bright fringe. This is the first dark fringe. Second, in between bright fringes there will be a dark fringe. So the fringe width means here the consecutive bright fringes or the distance between the consecutive dark fringes is called fringe width. How to get the fringe width in case of bright fringes or dark fringes? So here we know that exam here previously we have seen x d by d is equal to lambda. Okay, in this way for mth m order of fringe, if it is m, then we can say this is d lambda by small d, in put m before that. So this is the x distance of x, this one, the distance from the center bright spot. So for mth bright fringe. Now next, for m plus 1, the fringe order is m plus 1, then we can write m plus 1 into d lambda by d. Okay, so here the fringe width, how the fringe width beta we can represent with beta will come is xm plus 1 minus xm. So this distance x, the fringe, first, second, third fringes, and the distance is represented with x, is, if you subtract from this equation from this way, you get delta d lambda by small d. The d is that this distance between the interference pattern and the two slits. Okay, this small d is the coherence length, this one, between the two slits, the distance between the two slits is coherence length. So in the same way, the condition for fringe width, this is bright for bright. In the same way, the fringe width condition is calculated for the dark fringes also. So this will be coming out as the same value. This is for bright fringe and this is for dark fringe. So in the same process, by subtracting the distance of m plus 1 fringe from m fringe, the distance of the fringe width we can calculate. So for dark fringes also, the fringe width will be coming as a same formula. So in this way, we can understand the interference pattern by looking at the all the phenomenon what we have discussed. So this interference pattern has so many applications in physics. Okay, so in making some interference filters and mirrors, so it has lot of applications. So in the next class we will move to further topics in interference and their applications. Okay, thank you.